Hello guys, welcome to another video. In this video, we would be seeing on what is Apache Iceberg. So like in the market, we have like three major open table formats: Apache Hudi, Apache Iceberg and Delta Lake. So in this video, we'd be seeing what is Apache Iceberg, and I already have videos about Apache Hudi and about Delta Lake in my YouTube channel. You can refer them as well in case if you want to understand other open table formats. Okay. And the major reason why these open table formats have been very successful is because they have separated the data and the metadata layer separately, like in Hive. But in Hive, it's not an ACID, and in Hive, the schema evaluation and all these things are not supported. So here we have all these things supported. That's why they have gained a lot of attraction. And let's see some of the pointers and why open table formats have been very successful. The first thing is vendor agnostic format. That means like open table formats are not tied to any specific database vendor or a storage system. Instead, they follow the open standards and can be used across any data processing engines. That's why we call them as a vendor agnostics. And also we can use these open table formats with any processing engines like Spark, Flink, Presto and all. And also these open table formats are ACID transactions. Like if you take Hive, Hive is not an ACID transaction. So here we have ACID transaction. And the second major thing is like open table formats supports the schema evaluation. Like you can add, update a column, delete a column, update the partition and everything. And they are very efficient for query performance. And the next major reason is like they have the capability to time travel. For suppose you have updated anything in the production database, and in case if you want to go to the previous version, which is very difficult in the traditional databases, but we using these open table formats, as they store the snapshots. I mean, they call snapshots in terms of Iceberg, and in terms of Delta Lake, we call them as a versions as well. So using those snapshots or versions, we can go to the previous version of the table and all, even if the table got updated or anything. So these are the few reasons why these open table formats have gained a lot of attraction. So now let's go and see the structure of Iceberg. So we have an Iceberg table, and underneath Iceberg table is divided into two layers. One is a metadata layer and a data layer. Data layer is where the actual data files resides. And in the metadata layer, we have a metadata files which will have all the column level information, the data types and everything about the columns. And that is tied with the snapshots. We know, right? Like when we first time insert the data into a table, that will be one snapshot. And if we run some merge statement on that table, and then it will be a snapshot too, because the table has been updated. So these metadata files are tied with the snapshots. And then we have the manifest list and the manifest files. And if you see these manifest files, they are tied to the data files. Like what exactly does this manifest files does is, like it helps the query engines to quickly find out the data files needed, so that it helps like avoiding the scanning of the whole data. These manifest files will have the information of all the data files. So using this manifest file, we can get the information on which data files to read. This will also have the statistical information. Like this manifest files will have the statistical information about the data files, like what is the maximum value in this data file, what is the minimum value in the data file, and what is the order this has been sorted. I mean, the data file has been sorted in which order. All this kind of information will be there in the manifest files. And like this manifest list is nothing but it's like an high level metadata file that keeps track of the multiple manifest files. So we'll see everything in deeper, but on a high level, I hope we have understand how the Iceberg table looks underneath. So now let's see some of the pointers on the evolution of Iceberg. Okay. So if you see, Iceberg supports schema evaluation, like table schema level changes without rewriting the whole data. Like if you delete a column, or if you add a new partition, or if you update any column, if you rename any column, you don't have to rewrite the whole data. So now if you see, the schema changes are independent and side effect free. Iceberg uses unique IDs for columns to prevent data misuse. Like every column we create in Iceberg will underneath have an unique ID. So we can avoid the misusing of the columns here. So I mean, because of this unique ID, whenever we add or drop a column, it does not affect other columns. So now if you see partition evaluation, as I said, Iceberg allows updating partition layout in the existing table without rewriting the data. Let's assume, if you see, till here we have the data partitioned on month, but from this month onwards we have the data partitioned on day here. So the metadata for this till here will be stored separately, and the metadata for here will be stored separately. So we can avoid rewriting the data as the metadata for both is stored separately. So whenever we have the partition column change, we don't have to rewrite all the existing data. It will be separate and the new partition data will be separate. I mean, each data file will have the data ordered based on some column, right? So even that sort ordering of a column can also be changed in the Iceberg. And where does that sort ordering information will be stored, like minimum value in this data file and the maximum value in this data file? All that information is stored in these manifest files. So now let's check what is manifest files. Manifest files are used to track the data files in Iceberg table. So if you see this diagram, the data files are tied to the manifest files. So all the information about the data files will be there in this manifest files only. So they contain the metadata about the data files such as the location, size and the relevant statistics. Everything about the data files is being stored in this manifest files. And what is the metadata which includes in this manifest file? Like minimum and the maximum value for a column, the number of records and other statistics. So information is stored in this manifest file. So when we execute the query planning is done using these manifest files, and with which we can avoid reading the unwanted data. We can think like in the traditional databases, we have indexes, right? Like if we go to MySQL, we create indexes for the quick query performance. So these manifest files will act like an index in this data lakes. And also these manifest files can be compacted to group data files more efficiently in case if we have very small data files, and thus data files can be compacted into bigger data files because the reading of the data from very small data files is time consuming, right? So now we have seen what is manifest files. Now let's see what is manifest list. Manifest list is a high level metadata structure that contains the reference to multiple manifest files. It provides a consolidated view of the manifest associated with the table snapshot. So if you see here, for this specific snapshot, if we go to the manifest list will give the information on which manifest files we have to go to. That's a high level on the purpose of the manifest list. So this manifest list will just have the information about the manifest files only, and the manifest files will have the information about the table statistics, the minimum value, maximum value, the sorting order, and all this kind of information will be stored in this manifest files. If you see, the manifest list includes pointers to manifest files. So if you see here, this manifest lists are used to manage metadata at a snapshot level, facilitating operations like snapshot operation and metadata compaction. Like in case if the snapshot has to expire or if the metadata has to be merged, like as I said in the previous example where we have very small data files, and in case if you want to merge the data files into a single multiple bigger data files, so in that case metadata in this manifest files and the manifest list gets updated. So now let's look at the metadata JSON files. If you look at this diagram, we have seen the data files which is underneath the actual data and then the manifest files and the manifest. So now let's see what is metadata file. Metadata file, as the name suggests, it will just have the information about our table. That's it. Metadata file store the schema and other structural information about the Iceberg table. Okay. These files include information about the table structure such as the column name, data types, partition specification and the sorting order and all this information. So whenever there is a change in the table, a new metadata file gets created in the Iceberg. So Iceberg will have like a history of metadata files, so which is used for time traveling. With the snapshot is tied with this metadata file. When they both combine, we can go to the previous version. So if you see, Iceberg provides an option to automatically delete old metadata files to keep the metadata size manageable. Because whenever we have multiple updates on the table structure, in case if we don't want the previous version of this, we can delete the previous versions of the metadata files automatically instead of manually deleting them by configuring them in the table properties. So now let's see what is snapshot. Like if you see, like snapshots are the photos to our table. Every time a data is changed, new row is updated or added, or a schema is modified, a new snapshot is taken. And a new metadata file is also being created whenever we have an update on the table structure. In case if you see here we have two snapshots. That means the table, both the snapshots are tied to a single metadata file. That means here we don't have any table level changes. like the table name or the data type or the partition, all this kind of information is not changed. Just from S0 to S1 we just have the data level changes only. That's why they both are tied to a single metadata file. If you see, the snapshot records the state of the table at that moment and serves as a basic for the time travel queries. Iceberg uses procedures like expire snapshot to remove the old and unused snapshot, like because as we get multiple changes on the table every day, in case if we don't want the snapshots which are present every 1 week ago or 10 days ago, then we can expire those snapshots and those relevant metadata as well. And to time travel to the previous version, we need snapshots only. Using the previous snapshots only, we can get back to the table with the previous version. So now let's see what is the link between the manifest list and the snapshots. So if you see here, manifest list and the snapshot are tied. So let's check what is the link between the manifest files and the snapshot. So if you see, each snapshot is associated with one or more manifest lists, and these manifest lists contain reference to the manifest file that describes the data files included in this snapshot. So that's how the structure is. Like the snapshots are tied to the manifest list and manifest lists are tied to manifest files, and these manifest files will have the information about which data files it has to give based on the snapshot. So on the day one, when we have S0, they are tied to specific manifest list, and the list will have the manifest files, and this manifest files will are specific to the specific data files. Now we have some merge statement executed or some updates ran on our table. So new snapshot is created. That new snapshot is tied to this a new manifest list, to a new manifest file, and to the new data files under it, because the data has been updated. So that's how the table navigates whenever we get the new data. So now if you see, manifest lists help in managing the metadata for a snapshot by providing the structured way to access the manifest lists. So using this manifest lists only, right? Like it is acting an intermediate between the snapshot and the manifest file. The manifest files will have the information about which data files to go to based on the new snapshot. So as new snapshots are created, new manifest lists are generated to reflect the current state of the table. That's what I was saying. Older manifest lists associated with the previous snapshots are retained to support the time travel and rollbacks. So if you see, by linking manifest lists to a snapshot, Iceberg can efficiently manage metadata for the larger tables with many data files using this metadata only, this particular layer only. So now let's see for some of the maintenance operations which we need to know in Apache Iceberg. So like regularly expiring the snapshots is crucial to manage the metadata and delete unused data files, because when we create a table, there are multiple updates coming up every hour or based on the frequency of the table. So the older versions, like before 7 days or previous 10 days, snapshots is better to expire because they have no use, because we don't want to go back to that specific point in time of a table, right? So expiring them will help in managing the metadata and the queries quickly. If you see, expiring old snapshots removes them from metadata, making them unavailable for time travels. Like if we don't want them as well, as we are expiring those snapshots. So enabling write.metadata.delete after commit enabled helps automatically deleting old metadata files, keeping only a specific number of recent versions. And we have orphan files as well. In the next slide, we'll see what exactly is an orphan files. Okay. So if you see, small data files increases metadata and reduce query performance. The rewrite data files action combines small files into a larger files, reducing the metadata overhead as well. Manifest speed up query planning by indexing data. Rewriting manifest can regroup data files to better align with the query patterns. That's what I said. Like when we have smaller files, we have multiple manifest files and all, right? So when we have the bigger files, we have fewer manifest files, and it will be helpful in the query performance as well. Having a very huge data is also time consuming. Having a very small data is also time consuming. So we saw the orphan files. So if you see, orphan files refers to a data or metadata files that are no longer referenced by the table's metadata. All those which we don't use are called orphan files. So why do we get the orphan files? In a distributed processing environments like Spark, tasks may fail before they complete writing the data into file. This can leave the partially written files that are not properly registered with the table's metadata, and we don't use them as well. Okay. When snapshots are expired, the data files associated with the snapshots are typically deleted. However, if there are issues during the expiration process, some files might remain even though they are no longer referenced by the snapshots, right? Those kind of files are also called orphan files. The orphan files are nothing but files which are not used, and it can be a metadata files and a data files. Both can be an orphan files, and it's better to delete them because we know we don't need them, and that is also one of the maintenance thing which we have to do in Iceberg. And if we go with AWS S3 table buckets, everything, all these operations is handled by default by this S3 table buckets. So now let's look at the partitioning in Apache Iceberg. What is partitioning? As we already know, partition speeds up the query by grouping similar data together, like the data based on some time period, data based on some column, like a gender related column or whatever it can be based on the use case. So that data when divided into multiple splits is called a partition, which we already know. And Iceberg supports partitioning timestamp by year, month, day and hour level as well. And in Iceberg, we have hidden partitioning. So what is hidden partitioning? So in case if you go to the Hive system, whenever you query, we have to even add the partitioning column as well in the where condition, like select star from so and so table, where based on this condition, and the date created equal to so and so date. Then only it will query for that specific date only, because we mentioned that date. But in Iceberg, you don't have to mention anything in the where clause in your SQL query. Based on our SQL statement, it will decide underneath which partition to only query, and which using this metadata files and the manifest files, it will fetch only that specific partition data only based on the query. That's called hidden partitioning. User don't need to explicitly filter by partition column in the queries. That's what I meant. So now if you see, partitioning layout in Iceberg can evolve over time as the data volume changes without breaking the existing queries. That's what we saw here. We have partitioning on month here. Here we have partitioning on day. So the partitioning has been changed. The metadata for this will be separate. The metadata for this will be separate. So we don't need to rewrite the data here, unlike Hive. So now let's look at some of the performance in Iceberg. Iceberg is designed to handle massive tables, even those containing tens and petabytes of data. Even multiple petabyte tables can read from a single node without requiring a distributed SQL engine to process the metadata here. Like everything can be done in a single node, like all the queries can be executed in a single node, because we have the leverage of metadata in all these open table formats. This is achieved through efficient metadata management and scan planning, because the metadata structure is designed like that, right? Like first we get the structure from the, we'll go to the specific snapshot, we get the metadata for this metadata from the metadata.json file, and then we'll go to the manifest list, and this manifest list will help us to go to this specific manifest files only, and those manifest files will give us which data files to read underneath. So everything this can be done in a single node only. So now scan planning involves identifying the files in the table that are relevant to this query. Iceberg metadata structure allows scan planning to perform on a single node, which we already saw. So this is the few theory concept which I wanted to explain on Iceberg and what exactly is an iceberg underneath. That's it. Thank you so much for watching.